This video will just be finishing up some talk on PT diagrams. So in the last video I was saying that as we increase the pressure, the boiling, melting, and sublimation points generally increase. So I can show you guys that. Let me see, let me change my color here. Okay, so if I'm at a certain pressure, let's say it's right here, I can go across, see where I hit that line that has the melting point, and go down and say, okay, at that pressure, the melting point is about here. And if I increase the pressure to say here, and I go across, I hit the line, right? This is the temperature that kind of separates solids and liquids. That's the melting point. And I go down, and I'm here. And you can say, oh, so you increase the pressure, the temperature of the melting point increases. And you could make the same case for boiling, right, between liquid and gas, or sublimation between solid and gas. And I was saying that if we look at pressure, so at figure 2 now, if I increase the pressure on this solid, right, I've drawn lines to represent kind of the collisions from gas molecules around it. If I decrease the volume, which means I increase the pressure, I increase the amount of kind of force that's pushing down on the solid. And as that force increases, any molecule that wants to leave the solid, right, to have enough energy to become a liquid and to break off, needs more energy, right? Just because there's kind of force pushing it down, it'll need more energy to escape. And the same argument could be made between liquid and gas, right? So if there's more force pushing down on a liquid, the amount of energy a gas would need to escape, right, to rip free from all those intermolecular bonds will increase. So as pressure increases, the melting point and the boiling point increase because they need more energy at higher pressures to escape. And that's why water will boil at lower temperatures at high altitudes, right? And so it'll mess up cooking time. Or pressure cookers, which have really high pressure, will have a really high boiling point for water. So they can cook things at higher than 100 degrees Celsius with liquid water, which you can't do at lower pressures. Another thing, just kind of randomly here, is just to mention freeze drying. And for freeze drying, you generally have something that has liquid water in it and you want to get it out, but without heating the thing. So if I have liquid water here, you could see that I could decrease the temperature, right? So now that water would freeze, and then decrease the pressure so that ice, that solid, would sublimate, right? It would become gas. So you could go from liquid to solid to gas, right? To get all the water out, it would just kind of, the vapor would just kind of come out without increasing the temperature. In fact, you would actually have to decrease the temperature. That's just another cool thing to see on PT diagrams. Okay, and the last thing I wanted to talk about was water, actually. And so me drawing that kind of freeze drying thing up on this graph, number 1, was actually a little bit wrong because that's not what PT diagrams look like for water. And I kind of said normal up here because this is kind of generally what you can assume the general shape would be, right? And that's with the melting point and boiling point and sublimation point all increasing as temperature increases. Now, a more realistic drawing, though still bad for a PT diagram for water, would be this one. And the real important thing to see here is that this line here, right, the melting point line, goes backwards, right? It kind of goes off to the left instead of going off to the right. And the reason for that is, right, what this is saying is that I could go from a solid, to a liquid by increasing the pressure, which is weird, right? I'm squishing them closer together and it's becoming a liquid from a solid, right? That's weird. And the reason for that is, if we look at figure 4, is that ice, it just so happens that the crystalline structure for ice is more spaced out than the molecules in the liquid water, right? So it just so happens that this crystalline structure, where they're the most stable, where they have that very negative potential energy, has them actually kind of spaced out quite a bit compared to the liquid. And the liquid, they're actually closer. So as we're increasing the pressure on this kind of crystal here, I could kind of crush the crystal into the liquid, which is kind of backwards and weird. And remember, that is why ice floats on liquid water, because there's actually less dense, because the same number of molecules occupy a larger space, so it